Just a couple of announcements before we get started. Today is going to be a bit of a shorter class because all we have to do is talk about graphs of secant and cosecant. That is all we have left. On that note, class will also be canceled tomorrow just because we will have covered all of the material for exam 1. So how the rest of the week is going to go is today we are going to cover the graphs of secant and cosecant and how we transform those, do a couple of examples, and then tomorrow you will have no class. It will be a work day. You can email me questions, stuff like that. Thursday, we will have a formal review day for the exam. And then Friday, there will also be no class because you will be taking your exam. And how that will work, and I will talk about this more on Thursday, is you will have the entire 24-hour window on Friday, midnight to midnight Mountain Time, in order to take your exam. But once you start, you will only have a certain allotted amount of time. I haven't decided yet. It's going to be somewhere between an hour and a half and 2 hours. But you will have that amount of time once you start your exam in order to complete it. And what you'll do during that time is either print out the exam, or if you have a tablet or something you can write on, you can do that as well. Write directly on the exam, because you will need to write directly on it to do stuff like graphs, where I give you particular axes that I want you to graph something on. And then once you're done, you'll scan it somehow. You can either use an app like Cam Scanner. If you have a scanner, that works too, or just upload it directly from your tablet, whatever works best. You will upload that directly to the spot on the exam where it will tell you to. Are there any questions on that? Again, I will go more into depth with that on Thursday, but for now, that is the tentative plan. Speaking of the exam, you do have another homework this week, but because we have a test, it is due Thursday instead of Friday, because I want you to be able to get in all that practice before the exam, as well as I don't want you worrying about doing an exam and homework on the same day. That's never fun. So on the homework that is due Thursday, you may have seen it already. It is uploaded to WIO courses, but it is just practice with graphing. There are 6 problems, and it's just graphing with each different type of trig function: sine, cosine, tangent, cotangent, secant, cosecant. And we're going to cover how to do secant and cosecant today. Then you will have all the tools you need in order to do that. And I explain more on the homework, but it's going to be just like how you've seen it in class. For each graph, you'll have 2 sets of axes. One to do your prep work with, whether that be drawing a box or sketching in what asymptotes look like at zeros. There will be a lot more of the sketching and prep work that needs to be done today with the 2 graphs we're going to do today. But you will have 1 set of axes to do that, and that is important that you do those because those are a huge majority of your grade. It is how you're going to show your work. And then the next set of axes will be for the final prettied graph. So you will do those in your homework exactly how you've seen them done in the notes. And that's all that's on that homework, is just graphing. So if you have any questions on that, you can let me know. I'm going to make an announcement about this after class as well, but I'm going to move my office hours from tomorrow to today, just because class is canceled tomorrow. It would be easier, I think, to have things more set after class. So I will have office hours today as well as Thursday. But as always, if you need help, I'm always around if you need any extra help outside of those times. As a reminder as well, you have an Alex assignment due tonight, topics regarding graphs of sine and cosine. I believe there are 10 of those. So if you have not done those yet, make sure to hop into Alex and do that. Okay, any last questions on anything logistical or anything in general? All right, if not, then we are just going to hop into graphs of secant and cosecant, and that will be it for today. So let me share my screen really quickly. Come on. Is this working? There it is. Okay. Come on. There we go. Okay. So the last few classes, we've been talking about how to graph various trigonometric functions. We started with sine and cosine, showed the parent waves for those, and then how to transform them. Then use those to say, hey, tangent and cotangent graphs are just sine over cosine, or cosine versus over sine, respectively. So we can use that information to construct our parent graph and transform it as we have been. And we can do a similar thing for graphs of secant and cosecant, just thinking about what it means to be a secant or a cosecant. So what does it mean? If you recall, the secant and the cosecant functions are the reciprocal functions of sine and cosine. We call them the reciprocal functions. Just as cotangent was the reciprocal function of tangent, and all reciprocal means is just the fancy math word for we take a fraction and we flip it upside down. So if we have sine x over 1, the reciprocal function of sine x is cosecant because it's 1 over sine. Y is cosine over 1. We can always imagine everything being divided by an invisible 1. Its reciprocal function would be secant because we're just flipping that fraction upside down. So bearing that in mind, let's think about how we would graph these. So how do reciprocals work in terms of numbers? How do we think about what happens at reciprocals? Well, let's start with, the number 2. The reciprocal of 2 is 1/2 because we're just taking 2 over 1, flipping it over. What about pi? If you think about pi, the reciprocal is 1 over pi. What about 1,000? Reciprocal of 1,000, which is a fairly large number, is 1 over 1,000. So they get pretty small. What about the reciprocal of 0.1? The reciprocal of that is 1 over 0.1, but we don't like decimals in the denominator. So if you do this division, you can verify this in your calculator. The reciprocal of 0.1 actually happens to be 10. So when they start to get smaller or less than 1, the reciprocals grow. Okay, what about the reciprocal of 1? The reciprocal of 1 over 1 is just 1. So at every point on this graph where we have the point being 1, or if you think about it, the reciprocal of -1 is also just -1. These points on our tangent and cotangent graphs will stay the same. So these 3 points I just plotted on our secant, on our cosine graph here, those points will also be on our secant graph. We can do the same with the cosecant graph because we have a -1 here and a 1 here. We know that those points will be on the graphs of our reciprocal functions. Okay. Now, what if we think about, what's a good one to think about? We already thought about 1/2. And we know that on our graphs, we know that the cosine of pi thirds from our unit circle is 1/2. Okay, so that means on our graph, this guy right here, this value is 1/2. So to get what the value of the secant graph is, we need to reciprocate 1/2. So we know that the secant graph has a point here at 2 because that is a reciprocal of 1/2. We have the same kind of symmetry over here with pi thirds and negative pi thirds. That's 1/2 right there. So on the graph of the reciprocal function, we will be at 2. Okay, now think about the big important one. What is the reciprocal of 0? Well, that would be 1 over 0, which is a big no-no in math. We don't like dividing by 0. We can't do it. It's illegal. And just like what happened with the tangent and cotangent graphs, that creates asymptotes because our reciprocal values are getting larger and larger and larger as our values of sine and cosine get closer and closer to 0. So that means that wherever our sine and cosine graphs have a 0, like here, 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 etc., that we will have a vertical asymptote. So on the secant graph, we will have a vertical asymptote at negative pi over 2 and at pi over 2. Because that is where we are crossing the x-axis. That is where our cosine is 0. So when the cosine is 0, 1 over the cosine will be undefined and will create a vertical asymptote on the graph. So we can kind of start to see the shape of the graph forming. We will have something like this. This right here between these two vertical asymptotes will be what we treat as our principal interval for the secant graph. Thinking about principal intervals won't be quite as important for secant graphs, and you'll see why when we figure out how to graph these. But just know that we will be taking kind of copies of what's in here. And I say kind of because we also have this guy over here that's going to look like this, and this guy down here that's going to look like this. So essentially what we're doing is we're taking the peaks and troughs is what they're called, the high and the low points of the wave. And we are drawing shapes like this. And you can verify this mathematically if we think about like the cosine here of 2 pi thirds. The cosine of 2 pi thirds happens to be -1/2. So the cosecant or the secant of -2 pi thirds is just 1 over -1/2, which is -2. So this graph at 2 pi thirds will intersect to -2 down here. You can think about drawing more key points like that. The same thing happens over here with -2 pi thirds. But that is how the graph of secant is going to look. And we're just going to repeat this pattern over and over. That will make more sense when we do an example, but it's going to have that general shape throughout. Every time we have a high or a low point, the secant graph is going to come down, touch that low point at the peak, and then the functions are going to reciprocate as they go up until we hit asymptotes at the zeros of the wave. Same thing over here with cosecant. The function is 0 at -pi, so we're going to have an asymptote because 1 over 0 is an asymptote. We're going to have an asymptote right at x equals 0 and an asymptote right at x equals pi, because that is where we have zeros of the sine function. And then again, if we think about finding a couple key points over here in this quadrant, let's look at, for example, the sine of pi over 6, we know is equal to 1/2 by using the unit circle. So the cosecant of pi over 6, we reciprocate that fraction, we flip it over, so it's 2. So we know that at pi over 6, the cosecant graph is going to be 2. And the same thing actually happens at 5 pi over 6 because pi over 6 is the reference angle at 5 pi over 6. So we will have this shape. Same thing happens down here. The sine of -pi over 6 is -1/2 because the reference angle is still pi over 6. So when we reciprocate it, we need to go to -2. Same thing happens at 5 pi over 6. And then again, we have this shape. Does it make sense where these parent graphs came from? Knowing the parents exactly, and especially the reference points that I gave, like these guys here for secant and cosecant, will not matter as much when we get into how we're going to graph these. But the thing to keep in mind is the general shape, i.e. that we have asymptotes zeros, and that we have these little curvy parabola shape looking things coming off of the high and low points of the wave. Okay. Bearing the general shape of these parent graphs in mind, let's do an example. Oh, I meant to change the scale for this one too. Let me change this real quick. 1, 2, 3, 4. We could ignore this third set of axes. I don't know why it's here. Anyways, so I want to sketch the graph of -1/2 times the secant of pi x minus pi over 2. Now, the process for this is a little bit different than what we've done, but in the way it's different, it's actually very similar to graphs we've already done. So step 1 is to graph this guy, except to graph it with its reciprocal function. What I mean by that, the reciprocal function of secant is cosine. So what I want to do is to graph this whole thing, the exact same function, but instead of secant, I want to use the reciprocal function. I want to use cosine of pi x minus pi over 2. And to do this step, we just do what we have been doing all along. We use the 3 steps that we've been using on how to graph these. We draw our box. So what's the parent graph? It's cosine. So we know we're going to be transforming the cosine parent somehow. The amplitude is the absolute value of the factor, the multiplicative factor in front of the trig function. So the amplitude is 1/2, meaning everything will be 1/2 distance away from the midline. And the vertical shift, we don't have anything added to the end of here, so there is no vertical shift. So we know that we can draw the vertical parts of our box. Well, not the vertical, the horizontal parts on the Y, the vertical axis, at 1/2 distance from the midline, and the midline is at 0. So we know that we can draw the vertical parts of the box will hit somewhere here and somewhere here. It's going to be a pretty small box. Okay. Now step 3, that's where we solve that inequality. The principal interval for cosine is 0 to 2 pi. So we want to solve the inequality 0 is less than or equal to pi x minus pi over 2 is less than or equal to 2 pi. Add pi over 2 to both sides. We get that pi over 2 is less than or equal to pi x is less than or equal to 5 pi over 2. And then dividing both sides by pi to get x by itself, we get that 1/2 is less than or equal to x is less than or equal to 5 halves. Not 5 pi halves, 5 halves. And that was just what we got when we divided all 3 sides by pi. So that is our final answer. So we now know where to draw the x bounds of the box for our principal interval. We need to draw one line at 1/2, which is right here, and the other at 5 halves, which is approximately right here. So, oops, that is way too big. This right here is where we are going to place our transformed cosine function. However, we know that while the normal parent of cosine looks like this in the principal interval, we have to flip it upside down because we have a negative 1/2 in front. So we know that we're going to have these 2 points here at the bottom corner. Halfway through at 3 halves, we're going to hit here, and it's going to look something like this. Cool, that's all we need to know. Now, instead of using our second set of axes to draw the cosine graph all pretty like we normally would if we were actually trying to graph cosine, we just want to extend this all the way across these axes now because it's what we're going to use to sketch our secant graph. So I'm just going to follow the pattern, follow the size of the interval all the way through the graph. Like so. We know our final graph is going to look something like this. Cool. Okay, so now we have what the cosine graph would look like. We need to turn this cosine graph, we need to essentially reciprocate it. That's the fancy word for it. Before we do that, we're going to start by drawing in all of the asymptotes where the cosine function is 0. Because if you remember, our secant graph will have asymptotes where the cosine graph is 0 because we can't, if we try to reciprocate 0, we get an undefined nasty number, and that results in a vertical asymptote. So step 2 will be to sketch all asymptotes still on the same set of axes where the cosine function is 0. So get out a different color just to keep things straight. Now there's going to be a lot of them on this graph because that's just how this happened to work out. But it seems like at every whole number we cross at 0. That would have been more clear if I drew this more carefully. But halfway through the interval, we intersect here. So let's just sketch all of these in. Remember, on our final draft, we will have to label these. But for now, we can just sketch in where they are. Perfect. And you can verify this mathematically that at every single whole number, -4, -3, -2, etc., there will be a 0 on this function. You can just verify that mathematically. Or you can just, when you're drawing it, make sure that you include enough reference points to see where the things are 0. But for now, this is what we have. And then we also know the next step we need to do. We want to reciprocate. That's the fancy word. We're just going to reciprocate. And what that means is we drew in the asymptotes. That was part of the reciprocation process. But now what we want to do is just at all of the high and low points of our cosine wave, we draw in kind of what the shape of the secant will look like. So like that, and just do that like so. And now with this information in mind, all we need to do is just our final step, which is to draw the final graph. In other words, we want to transfer the parts of this graph that belong to the secant graph and not the cosine graph, and just draw it pretty and label our asymptotes. So we'll start by drawing in the asymptotes. I'll draw them in a less alarming color than hot pink. Let's try blue. We know those are going to go like this. And sorry, it's kind of tedious with how small this scale is, but it's nice to see what this function looks like when it repeats a lot. Okay. And then we know that we can use these points here over on this side of the graph to determine where the vertices of our points are here. So these labeled points here will stay the same. So we know we have a point at right between -4 and -3 at -1/2, right between -2 and -3 at 1/2, and then this pattern repeats. Okay, and now we just sketch in our curves like they were over here. And we know which direction they go depending on the interval because it was a high or low point of our cosine function over on the left. So we have those. Cool. Final step we need to do. I know there's a lot of them here and it's kind of obnoxious, but it's very, very important to always label your vertical asymptotes. So we have one at x equals -4, one at x equals -3, x equals -2, x equals -1, x equals 0, x equals 1, x equals 2, x equals 3, and x equals 4. So just however many vertical asymptotes end up on the scale of the graph paper you're given, you just need to label those. So the key to being able to do these is essentially just knowing how to do sine and cosines. If you know how to graph a sine wave or graph a cosine wave of any kind, you're golden because you just do that. Make sure to emphasize the high and low peaks of the waves. And then if you know what the shape of the cosecant and secant parent looks like, you just follow that. Are there any questions on how I got this graph? Okay, we're going to do one more example with the cosecant function, and then that is actually going to be it for today. Okay, so we want to sketch the graph of y equals -2 cosecant of x plus pi over 4. Okay, so to do this, first, what do? Well, we want to graph the same function except using the reciprocal of cosecant. So step 1 will be to graph y equals -2, and the reciprocal function of cosecant is sine. So we're going to graph -2 times the sine of x plus pi over 4. Okay, well, let's follow our 3 little steps. The parent graph that we need to follow is obviously going to be sine because sine, the amplitude is the absolute value of the value in front here. So the amplitude is 2. And there is no vertical shift because we have nothing added on to the end. You can have a vertical shift with these. We just have not happened to in either of these examples, but just know we could have a vertical shift. It would behave exactly as you would expect it to. The secant and cosecant curves would still intersect at those high and low points of the wave, regardless of where they are or where the midline is. So with that in mind, we know our amplitude to be 2 and that there is no vertical shift. So our midline is still 0. So we can draw the top point of our box here and the lower point of our box here. both 2 away from the midline. Remember, we will have to flip our sign parent upside down when we graph because there is a -2 in front, not a 2. But that is a problem for when we are drawing the parent curve inside of our box. Okay, final step. The principal interval for the sine function is 0 to 2 pi. So we are going to use that. We're going to solve this inequality. We want to go 0 to x plus pi over 4 to 2 pi. Subtracting pi over 4 from all 3 sides, we get that negative pi over 4 is less than or equal to x. It's less than or equal to 7 pi over 4. So a little bit less than 2 pi. Cool. This is the principal interval we're going to use for this function. So we can now draw in our x bounds. We start at negative pi over 4 over here, and we need to go to 7 pi over 4 over here. 3 pi over 2 is 6 pi over 4. 2 pi is 8 pi over 4. So we're going to go right in the middle of those two. Extend this just a little bit. And there we have our principal interval. Cool. We know that the parent graph of sine, if this is the midline, the wave looks like this. But we need to flip it upside down because, again, we have a negative out in front of our amplitude. So we're still going to start here. Instead of going up, we are going to go down. So what is, well, first, let's identify what halfway through our interval is. Halfway between negative pi over 4 and 7 pi over 4 is going to be 3 pi over 4. So that's going to be right here. We're also going to intersect 0 there. Halfway between 3 pi over 4 and negative pi over 4 is just going to be pi over 4. Instead of that being a peak, it needs to be down here because we need to flip the sine function upside down to look like this because of that negative sign. Okay, go away. Sorry. Stupid tiny eraser. Okay. So flipping that upside down, it's going to be down there. And then halfway between 3 pi over 4 and 7 pi over 4 is 5 pi over 4. We are going to have another peak up here at 5 pi over 4. And our principal interval is going to look something like this. Cool. Now, just like last time, we need to extend this graph of sine to the rest of our axes, which we can do. We can see here, we go at every pi, we intersect the x-axis again. So negative pi over 4, I intersect again at, okay, let me think about it. Okay, pi over 2 over, we hit a high point up here. Another pi over 2 over, we intersect the x-axis again. Another pi over 2 over, we're back down here. And so we're going to have something that looks like this. And then that doesn't hit a higher low point. Okay, so now we need to focus on step 2, which is where we sketch in all asymptotes. Where the sine function is 0. Because those are going to be the asymptotes of the graph of the reciprocal function, i.e. the graph of the cosecant. So we are going to have, let me pick a different color. Let's again do, I don't know, let's do red. We're going to have an asymptote here at 3 pi over 4, 7 pi over 4, negative pi over 4, and right here at negative 5 pi over 4. Those are the only 3 that are on this graph here. So those are the ones, or the only 4 that are on this graph. So those are the ones we're going to care about. And now that we have those, we can draw in our cosecant curves, just making little U's like this, stemming from the high and low points of the sine wave, i.e. the minima and maxima. Cool, and that step that I just did there was reciprocating. And finally, the last step, we want to draw the cosecant curves on the correct set of axes. Okay, so to do that, we just start by sketching in our asymptotes. So I said we have one at this point here, which is 7 pi over 4. Just going to label these now. We have another one here at 3 pi over 4. Going another pi over, we have one at negative pi over 4. Going up by another factor of pi. Finally, we have one at x equals negative 5 pi over 4. Cool. Now, sketch in where we know that we're going to have these vertexes of these parabola shapes. We know we have one right down. Well, let's start with the principal interval. We know we have one down here at pi over 4 and negative, oopsies, one down at pi over 4 and negative 2. Just halfway between those asymptotes. We know we have one up here halfway between 3 pi over 4 and 7 pi over 4, so 5 pi over 4, again at 2. Same thing, halfway through here at negative 3 pi over 4, we have one at 2. And then same thing down here at negative 7 pi over 4 and negative 2. Cool. Now we just need to sketch these curves in like we had them on our little sketch, just like so. Oops. Again, I'm not caring about any other reference points of the secant and cosecant graphs when I do this, like how up here I know I sketched this and this and this, but that was mainly just to get the general shape so we would know what these graphs looked like. Down here, once I have where the asymptotes are and where these points are here, that's all I really care about when I'm graphing these, because the general shape is all that really matters, and we know what the general shape is just given the asymptotes and the curves themselves. Okay, are there any questions on this example or on how we graph secant and cosecant graphs in general? Okay, I said this was going to be a short class today, and well, I meant it was. This was actually the last topic we have to cover before the Unit 1 exam. So you now have all of the tools you need to take exam 1 and finish all of the ALEX work in addition to the written homework that came out last night. So if you ever have any questions on any of it, please feel free to reach out to me. This is actually going to be it for class today, since we don't really have much else to talk about. But of course, if you have any questions, let me know. We can go over some stuff. And don't forget to work on your homework that is due tonight. Class will be canceled tomorrow. I will send out an announcement about that and about moving office hours. All right, if you have any questions, I will stick around for a bit, but otherwise have a wonderful Tuesday, and I will see you all on Thursday for some exam review.